Subtopic 1.4 is on chromatography, which is a broad technique, a broad set of techniques rather, that allow you to separate substances within a mixture based on some of their properties. Now, all the chromatography techniques that we're covering today all have two phases, so one stationary phase and one mobile phase. As the names suggest, one of them remains in place while the other one moves. And we'll cover that in more depth now. Now, the stationary phase in chromatography is the substance or the material that stays in place, and the mixture that we're moving through it will pass through and interact with it. Now, depending on the actual or the specific technique, you'll end up with in a different sort of form. So for TLC, which is thin layer chromatography, you end up with you have a thin layer of stationary phase made up of varying materials. Now for gas chromatography and high performance liquid chromatography, you'll have tubes with either completely packed with a stationary phase, like small tiny beads of them, or it'll be wall coated. So there's a tiny little hole through it, but the walls are coated in stationary phase. Now the mobile phase, again, as the name suggests, moves. So it's going to be carrying the mixture that we're trying to separate through or past the stationary phase, and it could be liquid. So for example, in TLC and HPLC, it's going to be liquid, but it could also be a gas if we're using gas chromatography. Now the important points, or the important, the important concept is the intermolecular interactions between the substances in the mixture and both the stationary and mobile phases. So when we want to separate some materials, we need those substances within our mixture to interact differently from each other with the stationary and mobile phase. So we'll get into more detail of that now. If you are putting substances or putting your mixture through the stationary phase, if there is a strong interaction between one of the components and the stationary phase, they'll essentially stick. So if you're moving a substance through and it attaches quite well to the polar stationary phase of this particular example, then it is going to take longer to pass through compared to another one of the components which perhaps is less polar and will interact less strongly with the surface and will instead flow with the in this particular case, flow with the non-polar mobile phase. The mobile phase is the substance that's going to be flowing the fastest. It's going to be moving, like there's going to be a bulk amount of material, like a whole bunch of liquid or a whole bunch of gas. It's going to flow, it's going to get to it's going to pass through the material, and depending on how well the substances in the mixtures interact with the stationary phase, they will move some proportion of that total distance that the mobile phase passes. Again, we'll cover a bit more of that in a little bit. So, in this, again, as I said, in this particular case, if you have a polar solute, so a polar substance that is dissolved, it will stick more strongly with actually, it's a good point. It says polar or more polar because it's not necessarily polar or non-polar. If you have a whole bunch of substances that are not very polar, but some are still slightly more polar than others, they will still behave similarly. If they're more polar or actually polar, they're going to interact with the stationary phase, slowing their movement, whereas the less polar or non-polar solutes will move through it with the mobile phase to a greater extent. Now, you have choices of the materials, so you can choose the stationary phase. Let's see if this works. Yep, you can choose the stationary phase and the mobile phase based on the particular mixture that you're trying to separate. If your mixtures are, the substances are mostly polar, then it's going to affect the choices you make. You're probably not going to have to actually choose many things, but you will have to recognize if someone tells you what we have a polar stationary phase, non-polar mobile phase, you are going to have to predict the polarity of the substances based on their movement through that. So if you have a polar stationary phase and you have a substance that doesn't move through it very quickly, it's going to indicate that it's the most polar. If you have a substance that moves more quickly through it, it indicates that it's less polar. Okay. Moving on to the next sentence, we have the data from these chromatography techniques can be used to determine the composition and purity of substances. And the subpoint is calculate and apply RF values and retention times in the identification of components in a mixture. Now, depending on the material, the technique, you'll describe the movement of your substances within the mixture differently. So first of all, we're going to start with thin layer chromatography, which is something we're going to be doing in the class in the lab. Now, they are rectangular plates. You can actually cut them out of larger sheets. You place mixtures on the surface towards the bottom of the plate. You mark where those substances are. So, for example, you'll mark that with, say, a pencil, something that is not going to dissolve in your solvent or your mobile phase. Ooh, there you go, I've made a mistake here. That should say mobile phase. Now, regardless, you place dots of your substance in a line. You mark that line. You have to mark that line because you may not be able to see. Let's say you have colored dyes. The colors may actually get dragged up completely, and you're left with nothing to show you where they started. So you have to mark that line. Now, after you place them into your solvent, your mobile phase, which I'll make sure, I might as well just change that right now before I forget. There we go. The solvent is definitely the mobile phase. So when you place that plate into the solvent or the mobile phase, you need to make sure that the solution is below the level of your origin, so below the level of your dots. If it is not, if you dip it in and the solution is this high, then what's going to happen is these substances are just going to dissolve into your solution, and they're going to be very weak. They're not going to move up. They're going to dissolve all the way in it, and then they're all going to move up all over the plate, and it's not going to be able to tell you anything at all. So, assuming we've done this, it will get this result next to it. So this indicates here, the solvent front, which is a new part. The solvent will move up using capillary action, so it'll essentially get sucked up the plate against gravity, and once it gets towards the top, not all the way to the edge, but towards the top, you pull your plate out so that no more solvent can get dragged up. If you go up to the top, you don't know when it actually reached that point, and so you can actually get movement of your solution up higher, even though your position at the end does not move. So if you finish it before the end, that way you have a very clear distance that the solvent has traveled that you can use to calculate your proportions from the other ones. So we have our TLC plate. We've taken it out of the solvent to make sure our solvent front doesn't move. We mark that solvent front with a pencil. Now, the reason why we do this is because even though you can see that the stationary phase is a bit wet, there's a color difference. When that solvent evaporates, this line will disappear, and so again, you will not be able to do the calculation if you wait too long. So if you mark the solvent front with a pencil, you have the origin with a pencil, you'll even circle each of these dots with a pencil, so that if you come back later and some of those dots are less visible, you'll still be able to calculate the proportion of the solvent front these components have traveled. Now, if we start with, we have our blue dot, and we place our blue substance in that first spot, and after it runs, it travels 2.5 centimeters. And so this distance is 2.5 centimeters compared to the 10 centimeters that the solvent front has moved. That we can use that to actually calculate what's called a retardation factor, which is essentially how much our substance has been slowed by its interaction with the stationary phase. Substance 2, so first of all, actually go back one step. The first substance appears to be pure because when it has moved up, it has not separated. It's moved, but it hasn't separated or resolved into multiple components. We started off with one dot, and we end up with this one dot. We end up with that one dot. Now, technically, it may not be pure. It may just be that the substances or the other substances in the mixture are invisible, for example, so they may not show up in visible light. It could also be that the polarity is so similar to each other that they don't actually separate within this mobile phase. They don't separate when they have this mobile phase and the stationary phase of the plate. But more often than not, the substances we're going to work with, you'll be able to see it if they are made up of more than one. Now, going back to number 2, it's traveled 5 centimeters out of 10. And again, there's only one substance. We started off with a green dot and we end up with a green dot. Now, substance 3, on the other hand, our black dot here, appears to have separated into 3 substances. So we have our blue dot just here, we have our green dot just here, and we have our orange dot just here. Now, the blue and the green are in the same position vertically as the substances 1 and 2 from our other 2 dots, but we have a new substance, our orange one, at 8 centimeters. So we have 8 centimeters up out of 10. So again, this substance 3 was actually a mixture, and we can tell that because it's resolved into 3 substances, each with different polarities. We know they have different polarity because they have moved a different distance up the stationary phase. And this technique separates things based on their polarity. Now, when it comes to it, I have left myself a spot which apparently I need to fill in. So, retardation factor is the proportion a substance has traveled relative to the almost messed it up again, to the mobile phase. So it's always going to be a ratio. It's actually fairly simple. I think I appear to not have tried to do a calculation, but if we just do it off to the side here, actually I might, I'll just use black. For this substance here, a better idea would just be using the colors that we came with, so I'll take a small amount of time to do that. So the RF value for substance 1 is literally 2.5 divided by 10. So it's traveled 2.5 out of the 10 that the solvent moved. So that gives us our 0.25. Now 0.25 is a quarter, and that's exactly what happened. Our substance 1 traveled a quarter of the distance of that our solvent did. Now similarly, again, I'll change the color just to match properly. Substance 2, its RF is equal to 5.0 out of 10, which is going to be 0.5. We'll just chuck a second significant figure on there just to be consistent. But that suggests that it's travelled half the distance of the solvent, which is the case. It's travelled 5 out of 10. And now we'll do the last substance, the orange one. And that last substance is 8.0 out of 10, which is 0.80. So that means our orange third substance that combines with substance 1 and 2 in the mixture with the represented by the black dot travels 80% of the solvent front, and that is the case. Now, if we were to rank the polarity of these substances, knowing that the mobile phase is non-polar and the stationary phase, the stuff that's on the plate, is polar, the thing that moves the least amount up it is the most polar. So the blue one, the blue substance 1. The green substance is next. It's less polar than the blue one, but it is more polar than the orange substance, which has moved the most. It is least polar because it's moved significantly with the non-polar mobile phase. Okay, so I think that's good. Oh, the only other thing was retardation factor is how much a substance has slowed, but that's not completely relevant for things like gas chromatography or column chromatography or HPLC, because we don't stop and look at the substances and how far they've traveled. Instead, we continually run those mixtures through until they come out of the system. So an analogy would be that if we just if we timed this run and just let it go until each of these substances reach the end, that wouldn't give us our retardation factor, but it would give us something like a retention time. For other things where you have for other techniques where you have our mixtures running through a tube that we cannot see through, we just let it run until it has reached the end, and in this case the orange substance would reach the end most quickly. The green would then reach the end, and then after some time the blue would reach it, and that amount of time it took to get through gives us an analogous result. It tells us how quickly it's traveling along, and so we get similar data. Now, this next part, we have ion chromatography, also known as ion exchange chromatography, is used to remove either cations or anions from a mixture by replacing them with ions of another type. Now, it says explain using equilibrium principles how ions attached to the surface of a resin can be exchanged with ions in an aqueous solution. Now, unfortunately, we haven't really covered equilibrium, yet, but we didn't cover it properly yet, but we did cover it briefly in the previous sections. Now, I'll explain using some equations what the hell is going on. So you have a stationary phase again, but it's what's called a resin, so like a plasticky sort of substance, and it has, as part of its material, it can bond to or attach to ions. Now, in this particular case, you have to load it up with a particular ion, and then when you run a mixture through it, the ions that were already loaded into the resin can be swapped with ions that are now in the mixture. So if you have, let's say, a particular ion that you have in your mixture, in your solution, that you want to remove, you can replace it with another ion that is less undesirable. An example would be some sort of, let's say, calcium or magnesium. You might want to remove that from water because it impacts the water hardness or how effective water is at cleaning stuff. And you could replace it with an ion such as sodium, which has less of an interaction. Yes, it's adding sodium to the water, but it's not impacting its ability to, let's say, clean stuff. So this equilibrium just here describes what's happening. If you have the resin, this resin which is solid and it's bonded to, so this here suggests there's a bond to the ion X+. If you interact that with ion Y, so Y+, another cation, what you can have is an interaction between the two where we end up with the resin bonded to Y instead, and it leaves substance X, like the ion X, to be free and aqueous as opposed to bonded to the resin. So this is our equation, our chemical equation, our equilibrium, and from our previous part, subtopic, we know that if we add in any of these components, so in this particular case, if we put in a whole bunch of Y plus, it's going to make this reaction move to the forwards, which will act to bond that ion Y to the resin, and it will remove X from the resin and put it back in, or put it into the solution. So, which is explained just here. Now, here we go. Now, let's hope I don't mess this up here. Anion exchange chromatography. Exchanges, oops, before I mess all that up too. Anion exchange chromatography exchanges. Oh, I don't even know what I'm meant to be putting in here. This is what happens when I make these early. Let's hope. There we go. Let's hope that's what I wanted. So we have anions are negative. If you see anion exchange, you are exchanging one negative anion with another negative anion. Also negative charge, negatively charged ion. Oh, here we go. There we go. I know what I'm trying to. Now I know what I'm trying to write. So scratch that. Anion exchange chromatography exchanges anions with a positively charged resin. Now, you can know this first of all because anion exchange is telling you that you're exchanging anions, and the only way for anions to bond, so if we look back up here, the only way for our positive, for example, okay, I should have done it the other way around, but either way, if we have a positively charged ion, which is a cation, the way it's bonded to the resin is because this is positive, the resin is negative. So in this particular case, anion exchange, you exchange anions by having a positively charged resin that they are attached to. Now conversely, cation exchange exchanges cations, and the only way for those cations to be exchanged is if the resin is able to bond to them, and the electrostatic interaction, positive and negative, happens by a negatively charged resin. Hopefully I haven't confused you there. I probably should have checked down all the way down here and remembered exactly what I wanted before I recorded this. So now it says here each ion will have its own affinity. Each ion will have its own affinity to the charged resin, resulting in characteristic retention times in the column. Now, what this means is if you have the resin that is loaded up with one ion, it is going to be able to swap out with a whole bunch of different ions. So in this particular case, for the example up here, assuming it lights up, if it's loaded up with X, it could be Y that you run through, but it could be some other positively charged ion, and it will still swap. They'll still swap over, but they won't swap over to the same degree. Some ions will preferentially bond to the resin or more preferentially bond to the resin compared to others. That can give you a diagram such as this one here. Now, you see the intensity, and I'll talk about the intensity more in a minute. But just assume that intensity, the higher it is, the more stuff there is. And the retention time here tells us how long it takes for our ions in this case to have eluted, or another word for that is to come out of the machine, exit the machine. Now we can see we have 5 peaks in this chromatogram. Chromatogram meaning our graph from our chromatography technique. Now I've said here, even that we've got 5 peaks, but it says here there is at least 5 substances. Now, like I mentioned a bit earlier, where we have our thin layer chromatography and our little blue dot, which looked like one substance. Technically, you could have more than 5 substances here, but that would mean that, for example, if substance 1, or the peak 1, was actually representing multiple substances, they would just have to have had the exact or very close interactions with the stationary phase as each other, so that their time that it takes them to get out, their retention time, is near or close enough to not be able to see the difference. So that pretty much says that here. Retention times for substances can overlap, which could hide different substances under the same peak. Not super common, but there are ways to work around it. Now, the amount of time it takes to come out of here tells us how strongly attached to the resin, or how strongly attracted to the resin the substance is. For example, if substance 1 here, it didn't take very long, only about 3 minutes to come out of the machine, which makes me think that it wanted to go with the mobile phase. It didn't really attach strongly to the stationary phase. Now number 2 is obviously attached. It took roughly twice as long, so it was more strongly attached to the stationary phase than number 1 was. And as we continue, we get all the way up to substance 5. Substance 5 took the longest to run through the stationary phase, which meant that it was probably attracted the most. So it took a long time to sort of flush it or push it through the machine. Now, it says here, as I just said, the order tells us how adsorbent the ion is to the charged resin. Adsorb means